Hello everyone and welcome to this new course in artificial neural networks. The course title would be Artificial Neural Networks Theory. I'll be with you, Dr. Osman Al-AGHA. In the beginning, I'd like to introduce myself, and I'll also be glad that every one of you would introduce himself and his objectives from joining this course. I want to tailor this course as per the objectives and requirements of all of the trainees. So to begin with, I am basically an electrical engineer with a PhD in electrical and electronics engineering. I've also done my master in business administration, so got both PhD in electrical and electronics and an MBA. I'm also certified as a project management professional. I've got my PMP. I'm also a Six Sigma Master Black Belt certified. I'm also a certified mentor. Over the course of my experience, I have been in the academic field and the training field for more than 15 years. Working as a professional trainer and university professor. I work also as a coach and a mentor for a long time. In the dynamic or professional field of engineering, I possess a robust background with over 20 years of experience as a project planner and project manager and an executive manager also. So you can say that my experience is a blend of the academic and the professional field. I also work as a consultant and the quality management field and also a certified auditor. So to begin with, let me just start with an introduction about this subject. So what do we mean by artificial neural networks? In a simple sense, artificial neural networks, or ANNs, are simply specified computers whose architecture is modeled to work some way or the other the same way or the same function of the human brain. Remember one thing, that neural networks can be both implemented in hardware or software. So like hardware implementation, we can use FPGAs, we can use ASICs, we can use TPUs, okay? And for software implementation, we can use a list of programming languages like Python, C, any type of programming language can be used, or most of the types of programming languages can be used in essence. So the ANNs typically consist of many hundreds or even thousands of simple processing units, which are wired in a complex communication network that resembles the human brain. So we are trying to mimic the human brain and mimic the function of the human brain. So we use the firing rules to fire the neurons, as we will see during this course, okay? And we'll see how these firing rules work, and we'll be using the neurons to classify different types of fruits, or two types at least of fruits, based on their size and length. So the strength of these connections, okay, or the weights, as we will see, okay, may be varied, or usually we vary to be able to train the network, so that the network will be able to perform different tasks corresponding to different patterns of the node firing activity. The structure is certainly quite different from the classic computers, and this makes our neural networks more intelligent than the classical computers. So here is the most simple structure of a neural network. Okay, as we can see, it consists of set of synapses. Okay, these are synapses with different synaptic weights. So every one of these synapses, or the inputs, okay, these are the inputs, like x1, x2, x3, x4. These are the inputs here. Okay, let me use this pointer, laser pointer. So every one of the inputs will be having a weight. Okay, like this this input x1 has this weight wk1 corresponding to it. So we can vary the weight of this input. We can also vary the weight of the second input, third and fourth input. Okay, and then we have also a bias to control all the inputs, also bk. This is a bias, we call it a bias, and we sum all of them in one junction, which we call a summing junction. Then the output from the summing junction is fed to what we call an activation function. Okay, and then based on the type of the activation function, we'll see all of this during this lecture. Okay, then we get the required output. So this is the summing junction, or the adder, which adds the inputs multiplied by their weights to the bias also with its weight. So the bias also has got its own weight. In a mathematical form, we can depict or describe the neural network in this form. U sub k is equal to sigma wkj xj, as j varies from 1 to m. So m is the total number of inputs. Okay, like in this case we have 1, 2, 3, 4, so we have 4 inputs. So m would be equal to 4, and the example in front of us. Okay. Then we can also represent the output y sub k as equal to phi u sub k plus b sub k. Okay, so it's just some function phi, which we defined as the activation function, multiplying this function with the both the bias and the UK, which is the sum of all the inputs, we can get the output. We'll elaborate this more. Okay, so we have VK is equal to UK plus BK. This is the output from the summing junction. I hope you follow up. The bias is an external parameter of artificial neural networks or artificial neurons and can be included into the equation as follows. So we can just make it one equation by here, as you can see, we start from 0 by including the bias. So instead of starting from 1, we have Vk is equal to sum or summation of Wkj xj as j varies from 0, okay, to m. Why 0? Because we include the bias now. So just including the bias, nothing more, nothing less. So we have Yk is equal to phi V of k, okay, and we know that the change of limits of j from 1 to 0. See, it was 1 before, but now it's 0. Why? Because we included the bias. It doesn't make any difference though. Okay, let's talk about the activation functions. We mentioned the activation functions. Actually, I want to just take a quick look about some very important or the most important activation functions. The first function would be the heaviside or threshold function. Sometimes it's called a step function, which is defined as follows. Phi of v is equal to 1 if v is greater than or equal to 0. Otherwise, it's equal to 0. Okay, so as we can see here, okay, for the whole interval starting from 0 to infinity, it is equal to 1. It has a value of 1. Otherwise, for all the other negative values of v, okay, the or less than all the negative values which are less than 0, the function of v phi of v is equal to 0. Very simple. So two choices or two conditions, just whether it is 1 or 0. Very simple. Another a bit complicated, not that much, but a bit complicated function is the sigmoid function, which is defined as follows. Phi of v is equal to 1 over 1 plus e to the power of minus a v. Okay, so this is the sigmoid function, as you can see. So is this function. It has different shapes depending on the value of a. So as we can see, a is the slope parameter of the sigmoid function. So as we increase the a, the function goes up, okay, so it goes towards something much similar to the step function. Why? Because if we increase a here towards infinity, this e to the power of minus infinity would be 0, so this would have a value of 1, so it will just have a value of 1. So increasing or decreasing the value of a will make this function differ in shape. So this is the sigmoid function. So let's talk about the single layer perceptron, which is the simplest model of neural networks. So the neuronal model we have just discussed is also known as a perceptron. So this is the simplest form of neural networks. So it's used, we'll be using it actually here for classification of patterns that are said to be linearly separable. So during this lecture, we'll just talk about the linearly separable patterns. We'll see what we mean by linearly separable. So basically, it consists of only of a single neuron with an adjustable adjustable synaptic weights and bias. So can vary the synaptic weights and we can vary the bias. Now let's take a look at the method of achieving learning, or how to learn or make it learn. Okay, what algorithm we use. So we talk about some variables, first of all, variables and the parameters. So some of the variables very important are the inputs. Okay, so the inputs x of n. Okay, so x of n is equal to m plus 1 multiplied by 1. So this is a vector actually. So this m is the number of inputs and 1 is the bias actually. Okay, so here again, this in vector form. Okay, we have the bias, which is 1. Okay, and then we have the number of inputs. We have x1 of n, x2 of n till xm of n, all transposed. Why we transpose make it take the transpose of the vector? Actually, because in normally it should be just a vector. Okay, so if we want to represent a vector, so it should be a vertical representation, not a horizontal. So it should be a column vector, not a row vector. Okay, but for simplicity, just to simplify and reserve the space, so we just take it as a column vector, but we just take the transpose. So to know that this is basically a column vector. Okay, so just for simplifying and preserving the space. The same thing we have for the weights. We have the weights of all the inputs plus 1, which is the bias. So we have, this is the bias, okay, this is the weight for the bias, B of n. Then we have the weights for corresponding to all the inputs. We have W1n, which correspond to X1n. So this is the weight of the first input. Then W2n, which is the weight of the second input, till Wmn, which is the weight of the mth or number m vector. Okay, so these are the weights. Again, this is a row vector here, but it should be, in a sense, it should be a column vector. So that's why we again take the transpose of the vector. So B of n is the bias. We also define y of n, which is the actual response. Actual response, we mean what response we get from the perceptron or from the network. Okay? The actual response that we get. While the n is the desired, what we desire. We get the desired after training. Actually, after training, the desired response should be the same as the actual response, okay? Or the actual response actually should be the same as the desired. So after training, we will make the actual response be equal to the desired response. Then we have AGHA, which is the learning rate parameter. So it's, in a simple sense, it's the rate at which we train the network, which is a positive constant less than unity. So it's something with a value between 0 and 1. How to define it? Actually, the less the value, the better the performance of the our network. Usually this is the case actually. Then we have the initialization, how to start, how to do the training. So we start by initialization. During the initialization we set all the weights to be equal to 0, then perform the following computations for time steps n is equal to 1, 2. These are iterations, or sometimes we call them epochs, how many times we repeat the computations. We will see this in the example in into more depth. Then the activation at the time step n. Okay, so how to activate the perceptron by applying the input vector x of n and the desired response d of n. Okay. Then the computation of actual response. So here we compute the actual response of the perceptron, and this is calculated like this: y of n, which is the output, is equal to sine w and xn. Sine is another activation function which is a bit different from the Hyperplane function, similar but different. Okay, sine, or sometimes called the Signum function. We'll see how to represent it. Here is the representation. Actually, Signum function or sine function has the value 1 for v is greater than 0. Okay, and equals 0 for v is equal to 0, equals -1 if v is less than 1. But for simplicity, and because we have only 2 classes in our example, we'll just use this function as if it has only 2 values, +1 and -1. Okay, just simplify it. We'll just neglect this condition or this value of 0 at v is equal to 0. So we'll treat it as if it is just a bipolar Hyperplane function. Then we do the adaptation of weight vector. So we have to modify the weight vector. So we have to update the weight vector of the perceptron using this equation. Wn plus 1 is equal to Wn, which is the previous time slot or timestamp, plus eta, which is the learning rate as we discussed before. All of this is multiplied by the difference between the desired output and the actual output. Okay, multiplied by the value of the input xn. Okay, and we repeat this equation whenever we have an error. Actually, our target would be to make this error. This is the error actually. Dn minus yn is the error. Whenever there is no difference, then we are all good. Everything is set. This is our target, to make dn is equal to yn. So we have, like for classification, we have d of n is equal to +1 if xn belongs to class C1. Okay, so we have 2 classes, C1 and C2, and equals to -1 if xn belongs to class C2. Then continuation, and we continue by incrementing the time step or time slot n by 1 and go back to step 2. We repeat from step 2 again every time there is a difference, okay, till we get no difference and everything is right. We'll see this in the example. We also define the decision boundaries, okay, or the decision boundary. So we have this, what we call a hyperplane, okay. Our target is to have 2 classes, class C1, class C2, separated, linearly separated like this, by this line. So to obtain this, we have our mathematical definition, okay, like this. So as long as we have 2 values, we can say that we have only two values. So we have only the bias, and we have I equal to 1 and I equal to 2, only because two classes. So we can say that from this equation, we can see that W1x1 plus W2x2 plus B, which is the bias, is equal to 0. So this is a linear equation. So this is the decision boundary for two-class classification. So let's take some example and see how this works. So let's have this example. We have two types of fruits. We can classify them like this. Class C1 fruit, which has, we have two samples, one having a weight of 121 grams and length of 16.8. The other one is 114 grams and the weight is the length is 15 centimeter. Both are classified into one class, which is C1. The other class with a higher weight, okay, which is 210 and 195, but the length here is 9.4 and 8.2. So different two types of fruits, okay, with different specifications. So this is the table which is representing the fruit, and we want to train the perceptron model using the above parameters to classify the two fruits. And after training, we want our neural network, the train network, to classify a new fruit with 140 grams and length 17.9 centimeters to see whether it belongs to class C1 or class C2. So if we just try to draw like this, the relationship between the weight in grams to the length in centimeters. So this is C1, okay, with these values here, okay. So this grams versus length, and this C2 also grams. These are the 2 points or 2 samples we have, and we can clearly see that we can draw a straight line between them to differentiate between them or separate them. So they are linearly separable. It's not always the case that our data is linearly separable. Some types of data are might be separated by a parabola, parabolically separated, or some other type of curve. Some of the data is very difficult, which we cannot separate. So at the beginning, we'll start by having some correct initial weights, okay? This is just for demonstration, okay? We'll start with some initial correct weights. We'll give W1 at time 0. We have to differentiate between this 0 and this 1. This is the first, this is the weight of the first input at the first iteration, or the first epoch, the first time to train, okay, as we start the training. So at time 0, okay, so we suppose that this is minus 30. So this is the weight of the first input, then the weight of the second input at also the first initial condition is 300, and the weight of the bias is equal to 50, and we assume our eta is 0.01, okay. So we have, these are, you see, these are the weights for the bias, 50, for x1 minus 30, for x2 is 300, okay. And as I mentioned before, I'll just assume that the Signum function or the sine function is equal to plus 1 for x is greater than or equal to 0, and equals to minus 1 if it is less than 0. So we, with the known conditions, okay, that we have, we can draw the boundary conditions and see if they are really, if it can separate. So we'll just, in our previous equation, we just plug in the values for the weights and the bias, okay, like this. So this is the first weight, minus 30, x1, and this is 300, x2, and this is the bias, which is 50. This is equal to 0. So this is a linear equation, so I can just find x2 if I assume some value for x1. So let's assume that x1 is 100, so we can, from this equation, we can find x2, and if we substitute the value, it will give us 9.83, okay? So, which is the point here, okay? And then, to draw the line, I need another point, okay? So, minimum, we need 2 points to draw a straight line. So, assume 200, okay, and plug in the values, we'll get this value here, 219.83. We just draw a straight line connecting these 2 points. So it's clearly now, that this line separates both the classes, okay? So all the points in this class are in one direction of the line, and the other 2 points are in the other direction of the line, separated by the line. So the initial hyperplane does separate the 2 classes efficiently. So this is good. So let's use these values to make sure that it's really defining, doing the job efficiently. Okay, so let's just plug in the values. We have these, the values of the x, which is 1 for the bias, 140. Okay, let's take the first value of the class C1. Okay, the known fruit, one of the known fruits, 140, and this is the weight, and this is the length, okay, other value of one of the fruits. And these are the weights. We have 50 for the bias, minus 30 for this x1, 300 for x2. This is given, actually, as we have seen, okay? These are the values given. So we now substitute in the function. Okay, y unknown is equal to signum of the multiplication of these 2 vectors. Okay, so we multiply this by this, so 50 by 1, and then minus 30 by 140, okay, and then this multiplied by this, okay. This gives us signum of 1220, and this is a positive value, so we can just get the value of 1. Any positive value will give us a value of 1. So a value of 1 will represent plus 1, actually plus 1 will represent C1, a value of minus 1 will represent C2. So this is plus 1, so it is C1. So this is right, because this fruit, 140, 17.9, this belongs to C1.